welcome to this week's Quant seminar. We have two talks today. Our first speaker is Stefano Ubbiali from ETH Zurich, Switzerland. Stefano obtained his PhD from ETH in the numerical, algorithmic and implementational aspects of the process coupling in atmospheric models. Stefano is currently a postdoctoral researcher in the group of atmospheric dynamics at ETH, working on the implementation of finite volume-based dynamical core for the integrated forecasting system of the European Center for Medium-Range Weather Forecasts. So without further ado, welcome, Stefano, and you may want to start the presentation.
Yeah, thanks a lot, Zongren, for the kind introduction and for inviting me. It's a great pleasure for me to be here and to have a possibility to present what I've done during my PhD, which I completed roughly 1.5 years ago, and also touching upon what we are doing now in the project where I'm serving as a postdoc. So to this end, I would like to mention that in the author list, there's Christoph Scher, Linda Schlemmer, and Thomas Schultes, who were my PhD supervisor, while Tiller and Gruber, Nikolai Krieger, Christian Kuhnlein, Lukas Pevritz, and Heini Werli are colleagues in the project where I'm working now. And also a special mention to the grid tools GT4Pi team. These two tools will be discussed a bit more in detail later. So I would like to start with a very short introduction about this structure of atmospheric models. So the starting observation is that the atmosphere is a truly multi-scale and multi-physics system. And this can be briefly seen also from this cartoon, where we represent some key atmospheric processes and their characteristic length and time scales. And we see that in space, we range from like centimeters to 1,000 kilometers, and in time, we go from seconds to days, weeks, and months. When you may know that essentially all atmospheric models discretize the lowermost portion of the atmosphere using prismatic grids, meaning that all vertical levels share the same horizontal discretization. And then, so every, let's say the community have like a common goal, which is like achieving 1 kilometer horizontal grid resolution globally. But even at this very fine resolution, which corresponds to an effective resolution of in between 2 to 4 kilometers, in atmospheric models, we still distinguish between two main components. So on the one end, we have features which emerge naturally on the grid and which form the so-called dynamics of the model, and which are addressed by a dynamical core, which is a fluid dynamics solver. And then we have also a series of subgrid scale phenomena which cannot be properly captured over the grid, and whose bulk effects on the mean flow is represented by so-called physical parameterizations, whose suite form this physics of the model. And then throughout representation, we are going to refer to the physics and dynamics as the components of the model. Now, the expression physics dynamics coupling, which is the main topic of this presentation, refers to the procedure which glue together the physics and the dynamics so to yield a cohesive model. And the topic has indeed received increasing attention over the last years as a side effect of this endeavor to decrease the grid spacing in the atmospheric models. Since the higher the mesh resolution, then the lower the error which is injected by each individual model component, and so a larger portion of the total error can be associated to the coupling. However, atmospheric models are inherently non-smooth, quite irregular, and they also, of course, address meteorological scenarios which are irregular by nature. And this means that theoretical studies, as the one that we will present later, are of course interesting and can provide a guidance, but they rely on assumptions which can be easily violated in reality. And that's why one needs to resort to numerical simulations. But on the other end, operational full-fledged models, one can argue that they are missing the required level of flexibility in the software infrastructure, so to investigate these numerical aspects of physics dynamic coupling. Indeed, historically, dynamical cores and physical parameterization have been developed in isolation for the sake of tractability. And this has led to components with incompatible structure, and this in turn hinder the share of code and knowledge between different research groups and different models. Moreover, the process calling sequences typically are coded for efficiency reasons. So all these factors add up so that past studies on the topic were limited to a few coupling algorithms. So the idea here is to tackle the problem from 3 different angles. So from a theory, application, and software perspective. So from a theoretical standpoint, we ask ourselves whether it is possible to make the total error shrink quadratically with the time step. So we are looking for the conditions which allow second order convergence in time. And we're also interested to know whether the process calling sequence plays any role in the second order condition, and whether enhanced accuracy comes at the cost of increase in instability. And then we proceed to substantiate our theoretical findings over an idealized model, which is, however, not smooth and irregular, so that we can see what happens when the assumptions underlying our theoretical framework are broken. And then all the simulations that we are going to present have been carried out in Python. And especially we are trying to design model components which can be composed in a plug and play fashion, which can be so used to form models with enhanced flexibility and modularity. And then we also, from a more software engineering perspective, we would like to know whether in terms of usability, productivity, maintainability, and performance, Python is a viable solution as the programming language for the next generation of weather and climate models. So starting from the theory, so you may know that weather and climate models are quite complex beasts. So they usually consist of tens of coupled nonlinear prognostic equations, which admit multiple formulations like hydrostatic, non-hydrostatic, Gaussianesque, and many others. And moreover, you can choose different variables as your vertical coordinate. Could be either pressure or derivatives, could be height, or could be mass. However, if we abstract away all the details regarding the formulation and the algorithms, we end up with the PDE, which is shown in the second box, where on the left-hand side, we have the time derivative of the state vector, where state is like the set of variables which identify the state of the atmosphere at any point in space and time. And this is given by the sum of 3 contributions. So we have the dynamics, D, we have a suite of physical parameterization, and then we have a source term, which is flow independent. Then if we make some additional assumption, so that the operators do not explicitly depend on time, or you can think of this as including the time in the state vector. These two are equivalent. If you assume that the external forcing is identically equal to 0. And if we neglect the space dependence, which is equivalent to like consider a problem after the spatial symetrization, then we end up with this autonomous and homogeneous ODE, which is shown on the lowermost box, and which is way more treatable than the starting formulation of weather and climate models. And then another ingredient.
Can I ask you, can you go back to the assumption that the operators do not depend on time? What does that mean? Is that separation of time scales, or what does that amount to? Quasi-static, quasi-steady. What kind of assumption is that?
It basically means that the operators depend on time only through the state, only through the input, and they do not have any parameter which is time dependent. And this is convenient for the following analysis, which we are going to do, especially for accuracy.
Can you give us an example? Can you give us an example?
Yeah, I don't know. You have like a turbulence scheme, which of course has a lot of empirical parameters, which they may be like spatial dependent, but not time. They do not vary in time. That's an idea.
If I have a storm, can that be true? If I have a storm, that's a transient, right? So
that is fine. So the solution, of course, can be time dependent, but the parameters which characterize the different operators in our analysis are supposed to be steady, which we can say that this holds for almost any parameterization except for radiation, where you need some way to model the diurnal cycle, of course, and then you have some time-dependent parameters. But like in microphysics, in turbulence, gravity wave, convection, the parameters are empirical, but typically are steady state.
Great, thank you very much.
Yeah, of course, if you have any other question, please stop me at any point. So coming back to the our framework, another second ingredient we need is a way to represent time integrators in a convenient way. For this, we introduce the numerical update operator, which basically digests the solution or the approximate solution of the current time level and produce the solution at the next time level based on the time step, delta t, and a set of forcing f, which represent the right-hand side of our homogeneous ODE. And similarly, we have also the exact update operator, which is U is the exact counterpart of E, which is in charge of moving forward the exact solution in time. And now the idea, in order to derive second-order condition, is actually quite standard and established in the numerical community. So we consider the exact and the numerical update operator starting from the exact solution and time n. And when we expand the two using the Taylor series expansion, and we can just write down explicitly the coefficient for the linear and quadratic term, and then we compare the coefficients term by term, and we set them equal in order to derive second-order conditions. And in this way, we derive second-order conditions which feature a high level of generality, as they are not influenced by the specific formulation of a governing equation, thanks to what we have shown in the slide before. They do not limited to any fixed number of parameterization. and they do not depend on the specific implementation of the time stepping, thanks to the introduction of the numerical update operator. When we have considered 6 different algorithms, and we have applied this kind of analysis to these algorithms, and now I'm going to list and describe them very briefly. So first we have the full coupling, which is about using the same time integrator to consider the dynamics and physics tendencies altogether, which is like the natural approach in that's like a numerical scientist will pursue when approaching PDE. When we have a what we call a lazy variant of this full coupling, where the parameterization are only evaluated once per time step, and they are kept fixed constant throughout the time step. And with war of interest for us, because this is the strategy adopted in the Cosmo model, which is the model used by the Meteorological Service of Switzerland. Now it's going to be replaced by ICON, by the way. Then we have we consider 4 splitting strategies where by splitting we mean that the dynamics and the physics are treated in isolation. So in the parallel splitting, each component is considered as it was the only active component at any point in time, and then the let's say intermediate results which are yielded by each component are combined together at the end of each time step, and this allows, of course, to process all the components in parallel from a software engineering perspective, and so reduce the need for data communication, data exchange. The most famous and most common approach are however, the sequential approach, either sequential tendency splitting or sequential update splitting, where the components are treated in isolation and one after the other, so that the output of each component is fed into the following component. And then finally, we have a symmetrized version of a sequential update splitting, also known as the strength splitting, in honor of its inventor, where each time step consists of 2 sequential update splitting steps, each act on half of a time step, but they consider the processes in opposite order, and this enables a 2-way communication between the processes. And this is indeed beneficial from an accuracy point of view, because provided that the operators are Lipschitz continuous, then the strength splitting and the full coupling are the only methods which are unconditionally second order, while all the other methods can be second order, but the conditions are quite strict, and so they are quite easily violated in reality. And we also ran stability analysis, where we focus basically on the capability of the coupling algorithms to preserve the stability properties featured by the individual time integrators used for all the individual components. And here we find again that the full coupling and the strength splitting preserve the properties, are like stability preserving as the sequential update splitting. The lazy full coupling, so it's cheaper from a computational perspective, but has some degraded both stability and accuracy properties, while in our experience, both the parallel splitting and the sequential tendency splitting were quite unstable. And that's why we are not going to show results for these 2 methods. And now coming to the application, so we have used as a benchmark for our framework and mountain flow model, where the potential temperature is used as a vertical coordinate, And we use this model to simulate vertical slice flows past an isolated mountain. So here on the right, you see in the top the velocity field after 5 hours of simulation. And we can clearly see the formation of a gravity wave developing like upward the mountain. And then in the bottom, we have the total amount of precipitation produced by this by the mountain. So the idea is that the mountain is capable of pulling water out of the atmosphere. And the model is quite simple. It consists of two main dynamic components, which are the horizontal advection where by horizontal we mean following the isentropes, and then we have the horizontal pressure gradient. And then in the physics suite, we have vertical advection, which here needs to be parameterized since the temporal variation of potential temperature depends on latent heat, and with again is related to the phase changes for water. Then we have the microphysics. Again, we use a very simple method called the Kessler or warm rain microphysics scheme. We have grid cell condensation, evaporation. We have sedimentation of rain. And finally, we have Zurich-like diffusion in order to add some implicit diffusion to the model. And then a short summary of our results is that the reaction of variables to the coupling is quite different between the dry and the moist variables. So the dry dynamics is weakly affected by the choice of the coupling, while we see that the convergence rate for the moist variables can actually adhere to the theoretical expectations, provided careful treatment of the grid cell condensation. And now I would like to spend a few words about this. So grid cell condensation and evaporation is about transferring water from water vapor to cloud water within each grid cell. In particular, we condensate water whenever we are the atmosphere is supersaturated, and this leads to a release of latent heat, while water is evaporated whenever we are below saturation, and this leads to absorption of latent heat. And this transfer of water between vapor and cloud water is most of the times addressed by some form of saturation adjustment, where it is assumed that this transfer happens instantaneously. And so we apply a direct modification to the QV and QC, which represent the mixing ratio of vapor and cloud water. And from here, we can then infer which is the heat rate, so that we can compute the variation in potential temperature, which here represents the vertical velocity. However, we argue that this approach is formally equivalent to a forward Euler step, which is only first order accurate. So this may spoil the convergence of the model, even if using a coupling algorithm, which is potentially second order accurate. So what we propose is to convert the adjustment into tendencies by introducing a condensation rate, so that these tendencies can then be integrated using high order methods. And of course, we must ensure that the basically the stability criterion is satisfied when defining this condensation rate, which in our simulation is just fixed in space and time, and has been chosen quite empirically, only for demonstration purposes. So we are not claiming that our the value that we have chosen leads to any physically sensible results. And then to test our ideas, we perform a self-convergence analysis. That means, we compute the root mean square error here for precipitation at different resolution, using as a reference a numerical solution produced by the same model, but generated using a grid spacing which is smaller than the smaller grid spacing used in the evaluation runs. In this case, is 4 times smaller than the Eiger's resolution used in our simulations. So in the plots, in both plots, we have the grid spacing on the lowest x-axis and the time step in the top, and resolution is increasing from left to right. We perform a pairwise comparison between the full coupling in red and the lazy full coupling in orange on the left, and while on the right we have a comparison between the strength splitting in blue and the sequential update splitting in cyan. And then solid line refers to simulation where we follow the prognostic approach to saturation, to grid cell condensation, and the dashed line refers to simulation using the established saturation adjustment. And what we see is that the solid, so if we focus on a single color, we see that solid lines is always below the dashed lines. So that means that indeed our proposal has an effect on the total error, so can decrease the error and can lead to a better convergence. And moreover, the two theoretical second or unconditionally second order methods can indeed achieve second order convergence. And while the other two methods are stick to first order, and actually when using saturation adjustment combined with a lazy full coupling, we barely converge. So that at the end, on the Eiger's resolution, we have that the second order methods can decrease the total error by 1 order of magnitude. Yeah, and now, as said before, all the simulations which we have conducted have been done in Python using bespoke library called Tasmania, which in its current form, it serves 3 main goals. So first, we extend an already existing framework called Simple to write model components which are either readable and which can be used as interoperable. And then we expose some utilities to write stencil code application, which are possibly performance portable. And in this sentence, there are 2 buzzwords, which are stencil and performance portability. So stencils are computational dwarf or patterns where each grid point is updated by accessing a fixed pattern of neighboring points, while by performance portability, we denote the capability to run on multiple computer architectures, reaching performance which is on par with native implementation. And then on top of this framework, we provide some concrete implementation of some concrete components which we use to write models with enhanced flexibility and modularity. Now, the idea of the following few slides is to walk you through some of the components which are available in the Tasmania framework and how they can be combined in order to write a model. So the means of communication between the components is the state. As we said, this is the collection of variables which identify the state of the atmosphere, and here is represented as a dictionary of data arrays, which are this data container, which are provided by the X-array package, and which allows to collect not only grid point values, but also some metadata like the units, by the axis, the coordinates, something like that. Then the first component we see is tendency component, which digests the state to produce tendencies, which are time derivatives for the prognostic variables, and also it can retrieve some diagnostics from the state. And similarly, we have a stripped down version of tendency component called diagnostic component, which only retrieves diagnostics. And then multiple of such tendency and diagnostic components can be combined or can be encapsulated in a concurrent coupling object, which combines the effects of all these of the wrap components. So the tendencies coming from different sources are summed up, and the diagnostics are gathered together, so that all these components can be called as a single entity. And then these, and then the tendencies produced by concurrent coupling can be used by tendency stepper, which is a time integrator, in order to advance the solution forward in time. And these components, this hierarchy of components have been designed with physical parameterization in mind. For the dynamics, however, we need something a bit more sophisticated, and this is because many dynamical cores adopt a strategy which is called partial time splitting, which is about using different time steps for different processes, so to have a time step which is better suited for the characteristics time scale of a process. So here we distinguish between three classes of processes based on their characteristic time scales. So we have this, what we call the slow physics processes, which occur on time scales which are a multiple of the main time step delta t. We have this fast dynamics and physics processes, where those timescales are comparable with delta t. And finally, we have what we call super fast dynamics and physics processes, which basically will require a smaller time step in order to be properly captured and represented. And then we introduce a new component called dynamical core, where basically the current state and the slow tendencies are provided from the outside, while internally the fast and the super fast tendencies are computed at a proper frequency in order to provide the state at the next time level. And then we have the couplers as a final step in our hierarchy, which combines the dynamical core and the physical parameterization represented as a tendency stepper here. So to yield a cohesive model. In this slide, we have as an example just parallel splitting, where we see the state at the current time level is forwarded to all the components, which provide some temporary states, which are the result of neglecting all the other components. And then these states are combined together to yield the final state, under the assumption that the time derivative for the total state is the sum of the time derivatives for each individual component. And thanks to the fact that that all components share the same interface, they can be interchanged, and this is quite convenient in our studies. And as a final observation, so we have this data array dictionary operator, which apply mathematical operation on the state and defer this stencil-based operation to some backends, which are in charge to actually performing the computation. And this is because Python is known for its expressive syntax. It's quite flexible, but at the same time, it's very slow. So it's intrinsically slow. So we need a way to overcome this slowness. And for this, all Tasmania components are accelerated by a domain-specific library for stencil applications, which is called GT4Py. So this is a tool which can generate high-performance implementation of stencil kernels, starting from an abstract and descriptive definition, which is given as a regular Python function and which is totally hardware agnostic. Then this definition is translated into a series, into a hierarchy of intermediate representation, which are tree-like representation of our computation, which are quite convenient to apply optimization on the code. And then the lowermost intermediate representation is consumed by the backends in order to synthesize code which targets specific purposes and architectures, computer architectures. At the moment, we have three backends. So we have NumPy, which generates NumPy code, and which should only be used for fast prototyping and debugging purposes. We have GridTools. So GridTools is a set of C++ libraries to write grid applications for weather and climate purposes. And by the way, so that's GridTools. Also, then it's the reason why the tool is called GT4Py, because it's for GridTools for Python. And then another backend that we have is DACE, which is a data-centric parallel programming framework developed at ETH. And then once we have a generated code, this gets compiled under the hood, and then we generate automatically Python bindings for this code so that the code can be accessed seamlessly from the Python level. And then we also perform.
Stefano, in the previous slide, when you have the code, the structure on the code, very nice on the right. So I see the vectorized Python, so that's like a fine-grained parallelism operations. But where is the this is sitting on many different CPUs or GPUs, but am I right? In other words, what is the parallelism, the outside parallelism?
So GT4Py is a tool for single node applications. Then for exchanging data between MPI ranks, then we have some other tools which were not used in the context of my PhD, but we are exploring and developing for the project where I'm involved now, and I'm going to say a few words later. But this is a very good observation. So there's no ALE exchange implemented, or which can be implemented inside the stencils. This is assumed to be a single node, or at least share memory.
But so the rest, you think you'll be doing it with MPI, basically standard MPI?
So not really. So we have as part of GridTools. So GridTools is at the core of GridTools. There is a domain-specific language, but in C++, and then there's like a constellation of other libraries which complement this DSL. One of these is called GX, which stands for generic ALE exchange for exascale application, which can perform ALE exchange in a way which is like fitted to the semantics of the domain. And now we are developing also Python bindings for this tool, so that can be used in conjunction with GT4Py, from the Python level.
So how big of a domain and what kind of resolutions you can do on a single GPU. Never, I mean, yes, it's very well organized and so on, but still you're limited, right? I mean, you mounted.
Yeah, we are limited. Yeah.
Yeah.
Indeed, that's why I limited myself to vertical slice simulation during my PhD. Because then, of course, you have way less points when you have a 3D model. Now, on a 3D grid, in the model that we are developing now, we can have like I don't know, 100 grid points per direction on a single rank.
Okay.
Yeah.
Yeah.
But then we can scale the application thanks to the tool I was mentioning, GX.
Okay, thank you.
Yeah. So the idea, would be to kind of integrate also the ALU exchange logic into the GT4Pi at some point, but this is, we are still very far from this level. Yeah, now, so as I was saying, we have performed performance analysis. So we compare all the different backends of GT4Pi and also to like state-of-the-art tools available in Python, which are NumPy and CuPy. And we use as a benchmark the three-dimensional extension of the mountain flow model, and we ran all simulation on a single node of the hybrid partition of a pit staint at CSCS. So the bars are colored by the coupling algorithm, and they are grouped by the backend. And please also note that the vertical axis is linear up to 60, and then it becomes logarithmic for visualization purposes. First, so if we focus on a single backend, then we see that the strength splitting is the most demanding from a computational perspective. And this is like expected because we are combining two sequential update splitting steps per time step. But on the other end, the full coupling in red is second order, but is as expensive as all the other splitting strategies, which are only first order accurate, while the cheapest is the lazy full coupling, because there we only evaluate physical parameterization once per time step. And then if we fix the coupling algorithm and we look at different backends available in Tasmania, then we see that thanks to domain-specific optimization with GT4Pi on the CPU, you can reduce the runtime compared to NumPy by a factor 20. And similarly, on the GPU, we gain factor 3 speed up when switching from CuPy, which is a GPU-enabled implementation of a NumPy API, to the GPU backend of GT4Pi. So this demonstrates that thanks to GT4Pi, we can overcome the slowness of a Python interpreter, and we can easily offload computation to GPU, just changing a single line in our name list. However, the question which I always got when doing such kind of presentation is, how does Python compare to Fortran? Because the Fortran language is still the preferred choice in atmospheric and climate modeling. Being 99.9% of models is written in Fortran. So people, of course, are willing to know how Python does compare to Fortran. To this, we have isolated a small scale demonstrator which is based on the Cloud C microphysics scheme, which is the scheme used operational at ECMWF. Well, actually, first I should mention that while at ECMWF, the main approach to incorporate physics in Python is to write Python wrappers around the original Fortran code, possibly GPU enabled using OpenACC. In Kilo, which is the project where I'm serving now as a postdoc, we are also exploring a full recoding of the physics in Python using GT4Py. And here on the plot, we have the runtime for this Cloud C demonstrator for different implementation, either in Python using GT4Py or in Fortran. On the x-axis, we have the number of vertical columns, and on the vertical axis, we have a runtime in milliseconds. And we see that if we compare the pink line, which is the optimized OpenACC implementation of the Cloud C, and the fastest backend of GT4Py, which at the moment is the DACE backend running on the GPU, when we see that we can actually beat Fortran on the GPU, and this is a quite promising result, while on the CPU, Fortran remains quite a tough opponent, and so there's still a gap between Fortran plus OpenMP and the fastest GT4Py backend on the CPU, but we are at least, say, competitive. Of course, there's still a gap, and this should be mentioned. And finally, a few more words about the Kilos project. So in this project, we are developing a Python implementation for the finite volume module, which is an alternative non-hydrostatic dynamical core, which discretize the fully compressible form of the governing equation, and which is based on the finite volume compact stencil discretization. And this is planned to replace at some point in time, while this is a candidate to replace the current dynamical core used operationally at the ECMWF, which is based on the spectral method. So the effort to develop a performance portable implementation for the FVM started 4 years ago, and now it's continuing with the Kilos project. And what we have at the moment is a fully ported version of the model on Cartesian grids, and we are developing the implementation for unstructured meshes. And the idea is that by redesigning completely the model in Python, we can design the framework, the software, to be flexible enough so to be able to implement different coupling algorithms and experiment with, for instance, also different process calling sequence. Yeah, so conclusion. So what we have shown is, from a theoretical perspective, is a framework which is centered around a template program where the physics and dynamics terms are purposely kept in an abstract form, and all the details are abstracted away. In this framework, we derive second-order cognition, feature a high level of generality, and we have shown that Eiger accuracy does not come at the cost of Eiger instability. Then we substantiated our results on simple models, showing that dry and moist variables react differently to the choice of a coupling, and that second-order convergence is achievable practically, provided careful treatment of the condensation. And then we have also presented the Tasmania framework, which is backed by GT4Py, which allowed us to run our resolution simulation in a reasonable amount of time. So based on our experience, we can say that Python is a strong and valid candidate as a user-facing language for the next generation of weather and climate models. However, I would like to finish by stressing that the physics dynamics coupling remains an open problem in weather and climate community. Indeed, our framework at the moment is limited to 2 time levels time integrators. So we need to extend it to multi-step if we want to consider multi-step schemes. It needs to be extended. We also assume that all the processes are treated using the same time step, but this is usually not the case in operationally, where usually some processes are sub-step, other are super-step. And also we only look at accuracy and stability, but there are some other properties which deserve attention, like mass conservation and positive diffutiveness. And we have used in our numerical simulation a very simple model. So the implication for a full-fledged three-dimensional model still to be investigated, and in this respect, the FEM could be quite a nice tool to play with. And it's of course not clear whether second-order schemes are appealing in terms of return to investment. And finally, yeah, as said, GT4Pi is a tool which only works on a single node. So we are now exploring how the GT4Pi code behaves at scales, which is the parallel efficiency provided by GT4Pi code. So this is me. Thanks a lot for your attention, and open to questions.
Thank you, Stefano, for your presentation. Yeah, do we have questions from our audience?
Maybe Raj
Yes,
can give us his opinion about the G4 4, GP, whatever T is.
Hey, Stefano, this is Raj. So,
Hi, Raji.
hey. So what kind of functionality GT4Pi offers, like grid-based operator like Laplacian, and do they offer for the unstructured grid also, or just structured grid? So
yeah, so the version 1 of the tool, which has been released just before Christmas, just targets regular grids, so structured computation, where we can directly access our neighbors. While a second version supporting unstructured grids is in development, has not been released yet, but yeah, it's under active development. But at the moment, we only support regular grids. Yeah.
And those APIs are accessible and the same, like through Python, and that can be generated for the GPUs and CPUs simultaneously.
Yeah. So the idea is that we have a single scientific source code, which is the code that the domain scientists deal with and interface. And then the tool automatically generates the code which then runs on the machine. So the code that you write for the stencil is not what it's going to run on the machine.
Okay.
It's what defines the logic which will be implemented by the code, by generated code. Yes. And
they are all for single node or single processes.
Yeah, single node. It's multi-threading and multi-GPU. Yeah.
On your slides, on your slide 17, you showed a comparison between Fortran OpenACC and the Python. So why the Fortran OpenACC is slow? Is this?
Yeah.
17? Yeah, just this one.
Yeah. So the point is that so OpenACC is a paradigm which is based on compiler directives. So and with directive, you can act on a single for loop, on a for loop level. While with a tool like GT4Pi, we have a possibility to analyze the full sequence of computation, and we can apply some domain-specific optimization, which allow to reduce the runtime at the end. So yeah, because these kind of tools are domain-specific in the sense that they are not a general purpose tool.
Mm-hmm.
They are quite limited to a very defined class of problems, but they can exploit the semantics and knowledge from the domain in order to do potentially a better job than general purpose languages like Fortran, for instance.
Yeah, because the same offloading you can perform through OpenMP as well, the GPU offloading for the Fortran.
Yeah, with so I would say also that support for OpenMP by the Fortran compilers, I think it is more solid than support for OpenACC and GPUs. Yeah. Why for the for compiling CPU code here we are using the Intel compiler for Fortran and the GCC for Python. But then for the GPU, we are using the NVCC compiler for native for NVIDIA GPU. So yeah,
because we are developing a Memphis software for Fortran. So I would like to look into this, like which would be the best way to do that, because that we are trying to do for the GPUs. So that's the reason I was just wondering why OpenACC is performing slow. So.
But the main also from a user perspective, the main advantage of DSLs is that you don't need to maintain multiple implementation of the same code, each targeting a different architecture. So
That's quite helpful. Yeah. Thank you, Stefano. Thank you very much.
So Stefano, you said that it's a domain specific, but has anybody used it in slightly different application? I don't know, the clouds modeling or the ocean atmosphere, interface or something?
Yeah, well, actually here the domain are stencil computations. So and of course, well, it's a bit tailored to atmospheric modeling in the sense that we assume that the vertical direction has a different meaning than the horizontal. But apart from that, can be used. So we have used GT4Pi both for the dynamics and the physics, and they work. So yeah, actually for the physics is even simpler because typically you only have vertical dependencies because they are single columns, so you don't have horizontal communication. But yeah, so also ocean modeling could be used potentially. Yes.
Yeah, great. Thank you very much.
Yeah, thanks a lot.
Thank you, Stefano, for your wonderful presentation.
Yeah, thanks a lot again.
No problem. Yeah, now we move to our second talk. Our second talk is given by Rambod Mojgani, who is a future faculty fellow at Rice University, developing data-driven and machine learning methods for modeling and data simulation in fluid flows, ranging from engineering to Earth systems. He received his PhD from University of Illinois at Urbana-Champaign in 2020, and his dissertation on reduced order models focuses on convection-dominated fluid flows, and it has received the Computational Science Engineering Fellowship of 2017 from the Granger College of Engineering, UIUC. Welcome, Rambod. You may want to start sharing your screen and start the presentation.
Yeah, thank you very much. Very excited to be here. Thank you for the invitation. Today, I want to talk about convection-dominated problems mainly, and how we can build causal manifolds to reduce the complexity of learning convection-dominated problems. So this work, some of it started in my years of PhD. So I'm going to be from UIUC that I'm going to talk about, but more recently, we have picked out the pin perspective on that at Rice. I'm interested in problems that are often can be described using partial differential equations. And more often than not, we have access to these partial differential equations, so we can solve them numerically. So what can machine learning do for our case in these problems? We are looking at machine learning here to generate ensembles of simulation accelerated, so we can build ensembles of simulations at low cost. So for uncertainty quantification tasks where we have limited access to hardware and we want to have real-time control. And this machine learning perspective is going to be very useful for us. In another perspective, sometimes we don't have access to these full equations. So we want to use data to learn this unknown part of our equations and learn the physics of the problem based on that. So I've noticed that almost always I'm trying to make a balance between what I learned from data and what I can include from my knowledge of the system into my ML solution. So it's going to be always a compromise between my theory and assumptions and the data model, data you can observe from experiments. And PINS was a framework that was proposed that well lives between this compromise, encoding the understanding of the system and partial differential equations, and also include data in a procedure for that. So first, I'm going to look at physics-informed neural network, specifically Lagrangian physics-informed neural network that we proposed. I know that PINs are most capable in this balanced regime, but I'm going to look here at PINs in a no data regime. So look at PIN as a solver only. This is not the best use case of PIN, and I'm not claiming that, but I'm solving the fundamental convergence issue at this regime. Then I'm going to look at the different side of this compromise, living in a fully data-driven model inside, but try to include some of my understanding of the system in building this architecture at this point. Finally, I got too excited, so probably I have too many slides here. If I get the chance, I want to talk about model error discovery with interpretivity and data assimilation. When we try to use the data to build a hybrid model based on our knowledge of the system and the working operational models that we already have for climate applications, for example, and trying to fill out the gap between our understanding of the system and using data. So in the first two topics, I'm going to be focusing on convection-dominated flows. So when I'm talking about convection-dominated flows, I'm talking about flows like figure A and B. In these videos, you see that there is a moving, traveling front, shock, or interface. So on the left, I have a rotating detonation engine. Its combustion occurs. There's a front in there, and the shock, oblique shock, originates from that and travels a large portion of the domain. On the right, there's a hurricane moving for kilometers, hundreds of kilometers. And the main feature of the flows are that there's a phenomenon that is moving long distances in my domain. And I'm going to posit that large Kolmogorov endwidth associated with these snapshots are going to increase the dimensionality of problem. It's going to be the source of many of the learning problems that we have for this kind of problems. So now let's look at the simplest convection equation you can imagine, just a convection equation in a 1D domain. W is the state parameter, so partial W partial T plus C, which is my convection speed. Partial W partial X is my first order space derivative. In a periodic domain between 0 to pi times 0 to 1 with a sign as an initial condition, I use the traditional 2019 version of the PIN. Nothing added to that, so I'm missing a whole bunch of technologies invented and novelties between that time and now. But let's just look at this problem for now. Minimizing the residual on the collocation points, initial points, and boundary points. The solution of this problem for C equal to 0 is going to exactly look like this, an identity. So neural network can easily learn this, and the error for this case is going to be low. I increase C to 10, I'm going to start seeing these convecting moving features. There is still a small, but if I increase C, then these convective features are swiping larger distances in my domain. I see larger and larger error in my pin, as described here in this architecture. If I look at the solution, the contour output of the pin I get at this point, I'm going to see, let me define. This high error and this non-converged solution here. So they called it in 2021 as failure modes of pin. You might agree with the name or not, but this is a phenomenon they're reporting, that the solution is not swiping through the domain. If I look at the residual minimization here, I see it in this portion. It's clearly the residual is satisfied. The boundary points conditions are mostly satisfied also. Probably there's a high error in my residual term in this region. And that's it. What has happened here is that my solution in future time steps is not being informed from the previous time steps. So there's a missing gap of convecting the information in my domain. And that is this kind of architecture in missing the causality in the problem. To be more precise, in convection problem, the causality is not even that the solution should inform the next time step. The upstream should inform the downstream. So what I'm expecting to do here is to find a way to have this convection be informed from the upstream on the characteristics lines, for example. So if I look at the literature, there are different suspects for this phenomena. Some people say this is because of the chaotic nature of the system. Convection is basically not a chaotic system very clearly. Some might blame higher order derivatives in the loss. Convection doesn't have any higher order derivatives in the loss. Some people talk about the stiffness of the system. Convection, even for high C, high convection speed, it is not stiff. Also, this concept is basically a numerical analysis related to the eigenvalues of the matrices, which I'm not concerned about that here. But there are also some reasonable doubts here. Maybe enforcing the boundary condition or initial condition and soft constraint is causing this problem, or the regularization of the composite loss we have and the competing factors in there. Some might argue this is sampling or collocation point distribution issues or optimization schemes. So I'm going to evaluate these as these suspects systematically, the traditional cases. So I'm not for now looking at the more modern developments. So let's first go with the boundary conditions. Here I impose the boundary condition, the periodic boundary condition as hard constraint. What we have to do is simply have a translation of coordinate system to a polar one. So I simply add one layer to my input to make sure that the boundary conditions are always satisfied. So if I continue with the practice that I described before, you see that still with hard enforcement of the conditions here, shown in red, I still for high values of C get these high errors. So let's for now conclude that enforcing the boundary conditions as soft constraint is not causing this issue. Now I look at the three more suspects here. Let's look at the loss terms here. I have loss on the residual, boundary condition, and initial condition. So I'm going back to the soft boundary condition and normalize them to have lambda r equal to 1 and have lambda for boundary condition and initial condition. And if I repeat my experiments for two different C for different grid types, a range of lambda, I get almost 400 simulations here. You see that still there are some cases that the error remains high. And also, it's important to note that I couldn't find one lambda that consistently give me a low error, especially for higher values of C. I could never get something even close to a small error. But for low values of C, I see these different modes of convergence, which some of the solutions is producing low error and some other ones are producing high error. So if I was to report the mean of these, probably I end up with a high mean error, and I cannot trust these solutions. So what can I do to remove this complexity from my problem? There have been several approaches proposed in this original paper. One of them is, they call it sequence learning, which is basically decomposing your domain to a smaller domain in time. The other one that they have proposed is curriculum learning, which is basically learning pin on a smaller value of C, then using that length weights to higher values of C, and using transfer learning to learn higher values of C and therefore more complex convection problems. So I've compared these methods here. Sorry, I have pin with soft constraint. I have pins with hard constraint of boundary condition. The sequence to sequence learning here, and the extended sequence to sequence learning, which is a mix of transfer learning and this domain decomposition here, and the curriculum learning here. You see that still it's helping with the convergence, and I get many samples that produce lower error. But what is the underlying mechanisms that has helped these solutions? How they have helped to reduce the complexity?
Rambod, have you used the causality weighting of Paris?
Yes, I tried that. I don't have the results here. I sent that to the reviewers, but the problem with that
I
is
was not the reviewer.
No. So I can send that to you separately. The problem is that that causality informing is forcing the learning in this direction, right? But in convection, I have to learn in this direction. So that looks like a washing down the equation.
There is also a paper by Ulysses Braunetta, who is doing a characteristic informed neural networks.
Yeah, I saw that in November, December, I guess. Yeah, I'm in touch with him. I realized that. So what he does is that he encodes the characteristic transformation before the layer, before solving for pin, right? So yeah, basically the same concept, different implementation and different idea. I think he has to have the closed form of the transformation there. I'm not going to do that. Clear?
Yeah.
Okay.
Thank you.
Thank you. So I'm going to describe where this complexity is actually coming from. And I'm going to try to convince you that it's because of the Kolmogorov n-bit complexity of the problem. So to define that, let n be a norm linear space, n tilde n is an n-dimensional subspace of n. Then Kolmogorov n-bit is defined as the distance between the solution and the approximation of the solution on this n-dimensional subspace. So basically, this is the worst error of the best representation of the solution in this space. So the rate of decay of Kolmogorov n-bit is known for some problems, but not for all the problems we have. But there are empirical evidence to show that Kolmogorov n-bit is correlated with rate of decay of singular values. So I relax my assumptions here and try to understand this phenomena through the lens of Kolmogorov n-bit by looking at the singular value of the snapshots, and try to explain these methods based on that. So for that, I have made a synthetic traveling shock problem. Here I have two values with this purple and yellow colors. So this is a translating shock problem. If I look at the singular values of this snapshot, I'm going to be looking at this decay. meaning that to reproduce this solution with this accuracy, I need to have this.
But for the benefit of everyone, so what you're doing here is like in POD, you take the method of snapshots and you find the eigenvalues of the correlation matrix, right?
Exactly.
And you say that is related to the Kolmogorov n width.
Yes.
Okay.
The connection between Kolmogorov n width and decay of singular values is not exact, but this is a good representation of looking at that. So what happens if I uniformly sample from this domain? I'm going to be capturing the large singular values exactly almost. So it's going to have the same rate of my singular values of the initial data. I'm going to, of course, lose some accuracy in the high singular values, obviously. But what happens if I sample around the shock? And this is something you have done before, and you have seen this, but probably let's look at it once more. So the rate of singular value decay in this problem is going to be, let me change the colors here, a bit faster than the original problem. So this is how this sampling is going to help me in convergence and having an easier trainable pin or any other neural network. The other approach here was singular domain decomposition. So look at the singular value decay of a solution that comes from domain decomposition. In domain decomposition, you are decomposing temporal domain in a smaller subsection or subdomain, and it is increasing the rate of decay of my singular values by far. So let's compare this, and you see the more I can increase the rate of value of the singular values, I'm expected to have an easier life trying to find a converged solution. So what's the optimal way of doing that? What's the best I can get here? The best I can get here is probably use the PDE and change my frame of reference and follow the shock. So my shock doesn't anymore look like a traveling shock. It becomes a stationary shock. And then my rank of metrics is going to be exactly 1. So I just have to learn one singular values or singular vectors. And this is going to help me to simplify my problem. So how to do this for PIN? By change of framework to Lagrangian frame of reference. So this is not the Lagrangian in the objective function, or it's not Lagrangian versus Hamiltonian. This is Lagrangian versus Eulerian frame of reference. For fluid people, it's very clear. Like when you move with the flow particles, this is called Lagrangian frame of reference. And let's look at that for convection equations, 1D here, where I have my general term for the convection, and I have my nonlinear diffusion also. I'm going to have the architecture, this hard boundary condition for the periodicity. What I have to do here is basically solve along the characteristics lines. So I will have one residual equation for X, which is my characteristics lines, another residual equation for a state parameter. So this is going to be describing how my characteristics lines evolve over time, and W is going to be my state parameters on top of this moving characteristics lines. So if you look here, I don't have convection anymore. I have removed the dependency of the problem to convection term. And that is going to help me to have an easier life training these pins or any other neural network. As for the architecture, I've kept one branch for just solving for W, another branch solving for X. I didn't have to do that, but I realized this is a very low dimensional problem, so I can probably learn that with a small number of the rates and biases here. So it's simple 2-layer would work for me here easily. I'm going to be minimizing the residual separately and the loss at the end. And this is going to be the Lagrangian pin for convection problems. So let's now go back to my convection problem. On the Eulerian grid, it's going to look like this that we started with. In the Lagrangian frame, I'm going to have partial x, partial t is equal to c. So X is going to be changing with a constant speed in time, and my state parameter is not going to change in time at all. This is going to help my L pin to have this error in red compared to pin. So in the low values of C, let me clear this. The L pin is going to have higher error, but for higher value of the C, the L pin is going to have lower error compared to the pin. And I have basically removed the dependency of my solution to convection speed. If I plot only the minimum of these values, my error plot is going to look like this line. And most of the error, notice that is coming from interpolation. I didn't talk about that, but the solution in the previous architecture is on the Lagrangian frame, right? And most often we want to have the solution on the Eulerian grid, so I need to have a post-process procedure here, interpolating from this time-varying grid to a time-constant Eulerian grid. So I'm introducing an interpolation error. Here I've used a simple linear interpolation, but probably we can use higher order interpolation to reduce this error even more. Now let's compare this with the methods that I previously described. I have pin with hard constraints. I have sequence-to-sequence learning, extended sequence-to-sequence learning, and Karukan learning. And let's add LPin to that. You see again that for higher values of C, the LPin is going to be more consistently converging to the right solution. And if you look at the error, they're almost on the fixed level. So this shows that the dependency of the error from C is removed from the problem. I can look at convection diffusion problem. So just adding the nonlinear diffusion here, the linear diffusion here, and different values of the viscosity, same story. I can look at Viscous-Berger's equation. So a nonlinear convection here. So my characteristic lines are not anymore a constant, they're proportional to values of the state. To impose traveling shocks instead of just a stationary shock, I'm adding a value of C to my initial condition. So with that, I'm forcing my shocks to move in time and travel in the domain, similar to the convection problem. Also, I can increase the value of the viscosity here, which makes my life easier, and see the results here. Then the question is how to do this for 2D. Easy. We are going to have two equations for characteristic lines in each domain, in each dimension. So this is one example: solution at the initial condition, solution at some later time step, and moving on. The solution of the pin at this time step is going to be hard to capture and high error. But if I solve my pin on these characteristic lines, I'm going to have any better convergence, lower error, and the solution is very close to the exact solution. Then the question is, how does it work where there is grid entanglement? So for the strong shocks, basically remove the diffusion from the problem. So again, here is the solution. As expected, I end up with a strong solution of implicit Bergers. A strong solution means that for example, this point, I'm going to have two solutions. And I don't know what the right solution is as of now. The first thing here is that I could get away with formation of this strong solution. My interpolation didn't have any issue. I could calculate the derivatives on this entangled and intersecting grid points. So there was no issue here. But as this solution is not physical, there are ways to get around it.
You just need to impose the entropy condition.
Yes. Next slide. I can impose entropy inequality, or I can have a TVD, or I can have artificial or vanishing viscosity and get away from that as necessary. So anyone interested, feel free to just try that, and I'm sure you get that solution. So here I talked about Lagrangian pins, how it is causality conforming for convection especially, and how pins can deal with grid entanglements with no issues. But now let's move on to the case that I didn't even have access to this governing equation. So in the balance that I started my talk with, now I want to look at the problem at a fully data-driven model. But let's say I know that the problem is convection dominated, and I want to impose some of my
Rambod, I have a question before you move on
sure.
to the next topic. I mean, this makes sense and it's consistent with the characteristic information, but what do you do for systems? What do you do for the Euler equations in 2D? Euler equations in 2D and 3D, even in 1D when you have multiple fronts. So what do you are you gonna do ALE that you say here, or are you moving with what speed are you gonna move to make it Lagrangian? Because you have shocks, you have shocklets, you have contact discontinuities. So it's not one feature that you need to sample better and to move on. That generality is generalization is always the issue. Generalization in the sense of realistic problems, because we all use these Mickey Mouse problems to bring out the issues, but the question is what you do for those systems, in multi-dimensions.
So the question, when there are too many features to follow, is the problem, right? Because if I have one feature, I can follow that. But what if I have too many features and they interact and so on, right?
Yeah, I mean, I asked the same question, Ulysses, in 2 and 3 dimensions when you have a system, an Euler equations. Yeah.
I don't think the problem there is to 2 or 3 dimensional systems. The problem is that there are too many things to track. There are too many fronts, and they interact with each other, right?
No, there is a problem, because you don't have characteristic. You cannot have characteristic information in 2D and 3D. It's only 1D that you have it. So you don't know which direction information is flowing in multi-dimensions in the system. So
there I will be trying to find a grid that follows some of these, but I don't want to impose this assumption of following these features. I'm going to try to learn the best frame of reference that can reduce the Kolmogorov width complexity, basically. So if I can define an arbitrary Lagrangian Eulerian framework, I probably can get away with some grid that produces a low-dimensional space or an easier problem to solve. I don't know if that makes sense or not, right? Then the question is how to do that.
Just one comment here. Hi, Rambod. This is Amir from Brown. I think even what George mentioned is for multidimensional or Euler system, but I think even for Burgess equation, if you just increase the frequency of the initial solution sine wave, and then you will get multiple shocks, and the moment with varying amplitude, and the moment they interact, your the characteristics breaks down, right? And then there is no way you can track these shocks after interactions.
So you mean the characteristics crossing each other?
Yes.
So these are not going to fix that issue, you say?
So basically in Lagrangian framework, it is difficult to track each and every particle in such a complex fluid flow scenario.
Yeah,
so,
when the complex is inside.
Exactly. So, So
then I'm going to be.
Yeah, please go ahead. Yeah.
Then I'm going to be looking for a grid that can follow some of them, but I don't want to impose to follow the particles. So I'm going to relax my assumption there.
Okay. Yeah. Thank you.
So maybe I get to the second part of the talk, and then then we can discuss if that is applicable for this problem or not. So again, So the motivation I designed my talk here is different than what you described. Let's go with that. But I think the method is going to be useful anyhow. Here I'm going to have the viscous Berger's equation in an autoencoder setup. So a converging divergent architecture and one STM to learn the low dimensional evolution of the solution here. So let's call this bottleneck to be sized KR. And train that on a snapshots looking like this. The solution is going to be reproduced as here, very close to the snapshots, and error decays as I increase the size of the bottleneck. But if I go into the extrapolation regime, the regime that I haven't seen the data even, my neural network cannot reproduce the results here. My shocks just stays stationary because they never saw the solutions here. Now I want to enforce this convection that I know from the system into my architecture. With that, I'm going to be looking for a map between my low dimensional space and high dimensional space. Let's start, my snapshots are on a space of M. And I'm going to be looking for a map G and G inverse from this high dimensional space to this latent space. So G here is an abstraction that takes my solution from the latent space to the high dimensional space. And I'm minimizing this error on the high dimensional physical space. I assume my solution here to be low rank. So I'm forcing my solution to be here to easy to learn. Moreover, because I know my solution, my grid is going to be evolving on a low dimensional space, that's some assumption that I am enforcing to my architecture. I can replace my grid size, grid decomposition, grid evolution with this decomposition. So now I'm going to have this low dimensional space on which my solution is low rank. And I'm going to be looking for this UXVX, which is the evolution of my grid. So back to your question, I think there I could learn such a grid that reduces the complexity of my problem. I would be happy to hear your comments on that. Or no, I can move forward with the slides. So this minimization problem is going to give me some UX and DX, but there are some problems here. For example, this does not guarantee uniqueness or existence of such low rank decomposition and vice versa. To make sure this exists or this solution is unique, I need to have a diffeomorphism constraint here. Basically saying that my solution, I want it to be one-to-one or bijective, and I can remove any grid entanglement by imposing this constraint. Also, I want this grid to be moving slowly in time or changing slowly with time, so I'm going to be penalizing that as well. And this can simply be done with the constraints that I add to my optimization problem. So I penalize every grid spacing, abrupt changes in the grid spacing by penalizing the first derivative of those grid locations, as well as fixing my boundary points so that they stay stationary. Now, if I go back to my Berger's equation, where I used to train my neural network architecture, I simply have to add one shallow layer before my architecture and do the practice again. Now, because I have enforced this constraint, I get lower error compared to the previous neural network solution. And you can see that in my error convergence. But also, because I know this low rank grid is representing my convection, I can extrapolate that in time. And therefore, my neural network is going to be capturing the convection underlying the problem. And I'm not stuck with this stationary shock anymore. And if I look at the error, this error is going to be much lower compared to the original neural network that I had. This is the dimensionality reduction approach. So obviously, it's going to help my convergence. So if I compare my traditional neural network with the proposed autoencoder, you see the errors converge much faster compared to the previous one. So here I want to say that large Kolmogorov NVs that is associated with convection-dominated flows is going to be a challenge for efficient and predictive data-driven models. But I showed some ways to incorporate some of these assumptions to our architecture to learn these phenomena easier and more efficient. I've shown that for projection-based reduced order model, which I didn't talk about it here. I showed that in a fully data-driven autoencoder-based reduced order model setup. I showed that physics-informed neural network. I think Simone showed similar results for DeepONet a few months ago. The same problem exists also if we want to do compressed sensing. There we are assuming that our solutions are on a wavelet space. Or if you want to do higher order schemes or system identification or data assimilation, we always end up with a matrix of high rank. And this matrix being high rank is going to cause some problems. Of the codes here for helping and low rank registration base, I can move on with the third step of my talk or wait for the questions here and discuss the problems that you just brought up or any other questions. Okay. So we talked about
Hi, Rambod. Can I
Yes.
ask a question? Quick question.
Sure.
This is Shahid Ahmed from PNL. Like for the autoencoder, how do you define the first layer that do this frame, like moving from the Eulerian to the Lagrangian? Is it trainable or non-trainable?
This is how I train it, right? This minimization problem is my training procedure. So the solution of this minimization problem is going to be that grid that I just talked about. So I learned it offline, separate from learning the autoencoder. So I have the data in, and then this is an unsupervised learning problem. So I end up with UX and VX. Now I can add this to my network, or you can use this as a preprocessor to do your data.
Okay.
And then put any architecture you want in the middle.
Okay, thank you.
So lastly, I want to talk about model error discovery with interpretability and data estimations. So here the purpose is keeping our operational models, the models that we are working on to do prediction, but using the data coming to our from observation or experiment to learn the difference between the system and our prediction. So basically consider the system in this form. And let's say I have a model of the truth, which represents most features of the truth, but there's still something lacking from the system. The model error here is defined as the difference between these operators. So I want to learn this H function that represents the difference between these two models. So what I do, I initialize my model from my observation of the system. I evolve them for some short time period, and I end up with a difference in time step in the prediction. I do a sparse regression problem here to find the which linear combination of my bases are going to represent the missing error. For that, I'm going to use relevance vector machines, and I don't want to talk about the details here. You can find you can find that in this paper. But the point is, because I didn't get rid of my model, I can use many of the technologies to remove noise dynamically. So here we have used Ensemble-Kalman filter to remove this noise optimally. Here today, I want to just show some perspective on how we can deal with the missing observations for a turbulence flow and what is the main challenge of that. So I have a quasi-geostrophic flow, a highly turbulent flows, And there are often calibration problems that we want to find these coefficients. With a provided setup, I can find that, or I can find some external forcing on the problem. This is more visual, so I'm going to just be looking at this case. If I have a reference and I have the model, with this problem setup that I defined, we can fill out the corrected model easy. But how do I can deal with the missing problem, missing data points? So I'm going to train a neural network on the observations that I have, which is gappy. There are missing points in that. And now that I have trained this neural network, I can query that in any points of the domain that I have. And then I'm going to end up with an interpolated solution. So it seems easy to do. So let's do that for some state variable. So I'm going to be looking at the state variable psi, its first derivative and second derivative in the spectral domain. If I do that, I'm going to end up with a gap between the output of the neural network, the interpolated data learned, and the solution, which is going to mess up the whole discovery procedure. This is even worse for first and second derivatives, because when you take derivative of the noise, this is going to be even higher and higher. And that is known, and your group has worked a lot on this. It is a spectral bias innate to training of a neural network, right? But I want to show how this is even a more harder problem for the turbulence compared to computer vision tasks. So let's just compare some of the benign looking states of the system and compare to that with a complicated looking natural image in the spectral domain. You see here the gray line is corresponding to decay in the natural image, but this black line and this red line are corresponding to decay in the spectral of the state parameter. So these states look very easy and less complicated than this box. But if I look at this spectral domain, I see it actually has more scales to it. There is a higher range or wider range of the features that has to be learned for a turbulence flow compared to a traditional natural image or a class or whatever we see around us. So this is absolutely more important for us as turbulence people to be able to capture this scale and this multi-scale features of the flow. So here I've used random Fourier feature. Simply we add this as a layer, non-trainable, to our architecture. And now I can learn this interpolator much closer, representing the solution even in the higher wave numbers. And with that, I can use this for any discovery that I have. To end up, I tried to find the right balance between my assumptions, theory, and also what I can learn from data-driven modeling. Sometimes I had to incorporate some of the assumptions I have so I can learn easier from the data to learn what I don't know about from data. And sometimes I had to leverage theory to be able to learn from data. With that, I open the floor for any more questions, and I'm going to be happy about discussing any of these or something.
See a question from Hamid. Hamid, you can ask your question. Yeah.
No, I was just clapping, so I didn't raise my hand.
Clapping, okay. Clapping. Okay, great. Well, Hamid, where are you from?
I'm from actually Rice University, but I'm in Boulder, so I'm hostile.
So you're related.
To some extent.
This was an insider plan.
Insider. It's still okay. It's still okay.
Yeah.
No, I was wondering, Rambod, how the answer to the reviewers, which I as I said, I was not a reviewer. What did you see? What did you see when you compare with the casualty weight training of Paris versus your Lagrangian approach? It could be very similar, but I was wondering actually what quantitatively.
Yeah. I wish I included that in the
just
slide,
describe, just
but I can say that to you. Yeah,
with your pencil, you can draw it. I'll believe you.
So let me go back to this contour and how it looks. Okay, it's taking too much time. Maybe this is faster. So, but I saw that these convection features, instead of going in this direction, they more go in this direction. Because what they do is that they force the loss in such a way that the previous time step is influencing next time step, right? Yeah. So it's going to be look like it's washed down.
Right.
I don't know if I could explain like how they look, but imagine you have a picture with color paint, water paint, and you have washed it down with this direction.
Yeah.
So that's why for it to be causal, we have to make sure this is going from direction of the flow.
But in terms of the accuracy on that right plot, where are they compared to you?
Oh, so they couldn't learn this problem. It makes it worse.
Okay.
I didn't search for the whole range. I picked 1C equal to 30 probably.
I hope that he's not a reviewer.
So I learned a lot from that paper actually. That was the idea of that this phenomena should be satisfied, come from that, right?
I mean, the method is more general, so it doesn't need to have, characteristic information, just even for parabolic equations. And the Kuramoto-Zhivajinsky that they have, I think it's pretty tough example.
Yeah, they didn't show the results for convection. I don't know if they were not interested in that or they tried that. I have no idea. At least I couldn't make it work. I tried they have different hyperparameters. I played with that a little bit and couldn't get that to work.
Yeah. Okay. Thanks for coming, Rambod.
Thank you for the invitation. And thank you for the insightful comments. I'm going to think about that probably more.
Yeah, do we have more questions for our speaker from the audience? All right, thank you, Rambod, for your presentation today and for attending our seminar. And okay, so this comes to the end to our this week's current seminar, and everyone has a good weekend. I'll see you next week. Bye.
Thank you.